Hello everyone and welcome back to the final video lecture for statistics, and today we are going to be testing the population correlation coefficient rho. So we are going to be using sample data and a sample correlation coefficient to test the significance of the population correlation coefficient rho. So we're going to use this example that we ended with the last video. Here we had a whole bunch of pairs of data, and using a graphing calculator we got an R value of approximately 0.979. Now remember, R is the correlation coefficient of the sample. So this number is pretty decently close to 1. I mean, this is a really strong positive linear correlation just by looking at it. So this is just for the sample. The sample data has a pretty strong positive linear correlation. So what we're going to do is we're going to use a couple of different processes to test whether this sample data is enough evidence to say that the population also has a strong linear correlation. So that's what this process is going to be about. So once you have found R, the correlation coefficient of the sample, you want to decide whether that sample data is enough evidence to state that the population also has a correlation that is significant. So you're using your sample data to conclude whether or not the variables in the population have a linear relationship or if they don't. So there is always a chance of making a wrong decision, as with any other hypothesis test. This is what's called the level of significance. The level of significance is the small probability of making a wrong decision, usually set as alpha equals 0.01 or alpha equals 0.05. And then it will be the probability that you will decide that the correlation is significant when it really isn't. So in order for a correlation coefficient to be significant, its absolute value must be close to 1. Now, how close? There is a mathematical way to determine how close is close enough to be strong using what are called critical values. And the critical values are actually in a separate table. The table is called the critical values for the correlation coefficient. I will upload this table onto the Canvas Chapter 9 module so you can access it there. It is also located on Canvas under the Files tab, under the Tables folder. And you can access this, it's called Table 11, in MyStatLab itself, and you will be able to access a picture of this table on your MyStatLab homework. But once you get the critical value out of this table using a process I'll show you on the next slide, if the absolute value of R is greater than your critical value, then your correlation is significant for the population. If not, there is not enough evidence to conclude that the correlation is significant for the population. Now, keep in mind that just because there is a significant correlation does not mean that there is a cause and effect relationship. All you are saying is that there is some sort of linear relationship. You don't know why. Nothing about this test will tell you why that relationship exists. You just will know that that linear relationship exists for some reason. More research and in-depth study would be needed to determine a cause and effect relationship. So this is a snippet of what that table looks like. We have n here, which are the number of pairs of data. And then we have various alpha values, 0.05 and 0.01. Those are really the only two alphas that we're going to use for this. So in that Old Faithful example, we used 25 pairs of data to find an R value of approximately 0.979. Based on that sample data, do we have enough evidence to conclude if the correlation coefficient is significant for the population? And we're going to use an alpha of 0.05. So n is the number of pairs of data, so n is 25. So we're going to go down to an n value of 25, so we're going to go to this row here. And the column that we're going to look under is alpha equals 0.05, so we're going to use this column here. So going under the alpha equals 0.05 down to 25 pairs of data gives us this as our critical value. So our critical value is 0.396. So then what we're going to do is we are going to compare the absolute value of R to our critical value. So the absolute value of our R, the absolute value of 0.979, is equal to 0.979. So 0.979, we're going to compare it to our critical value, 0.396. 0.979 is greater than 0.396, so the absolute value of R is greater than your critical value. Since the absolute value of R is greater than your critical value, your population correlation coefficient rho is significant. So what this means is that this was enough evidence to conclude that there is a strong, significant linear correlation between these two variables for the population. Now that's just one way to test for the significance of the population correlation coefficient. So you can either use your critical values that come out of that special table. Another method for testing the population correlation coefficient is to use a hypothesis test. So this is going to be the hypothesis test, basically in the exact same process as we learned about in Chapter 7. However, in this particular instance, since we're testing correlation, you're only going to have these H0 and HAs. So for H0, rho is going to be equal to 0, which means there's no significant correlation. And then your alternate hypothesis HA is going to be rho is not equal to 0, meaning there's no significant correlation. So we're going to be using a two-tailed test for this because HA contains a not equal. And this is actually going to be a t-test. So we will be using a t-test for the correlation coefficient, which means we're going to be using the t-distribution. So we are going to be using the test statistic R. So the sample correlation coefficient R will be our test statistic. And the standardized test statistic will be a t-score. And to turn your R into a t-score, it's this formula. It's gross. This is the formula to turn your test statistic your test statistic R into a standardized test statistic, a t-score. And remember, this is used to test whether your population correlation coefficient rho is significant. Now, this is a t-distribution. If you remember, the t-distribution needs degrees of freedom. R, however, comes from a paired data set. There are two sets of data paired together. So your degrees of freedom is actually going to be n minus 2, where n is the number of pairs of data. So you're going to take the number of pairs of data, subtract 2, and that will be your degrees of freedom. So here is the process in words to using a t-test to test the population correlation coefficient rho. You're going to state the null and the alternate hypotheses. The null hypothesis will be rho is equal to 0, no significant correlation. The alternate hypothesis will be rho is not equal to 0 or a significant correlation. Then you're going to identify the level of significance, alpha. Then you're going to find the degrees of freedom, which is n, the number of pairs of data, minus 2. We're going to be using rejection regions for this. So we're going to be using the t-distribution table to find the critical values t0 and negative t0 that go with your alpha and n minus 2 degrees of freedom. You're then going to draw a sketch of your distribution, put in your critical values, and shade your rejection regions. Then you're going to turn your sample correlation coefficient R into a t-score using this formula. Then you're going to put your t-score on your distribution and make your decision. If t is in your rejection region, you are going to reject H0. If t is not in the rejection region, you're going to fail to reject H0. Remember, if you reject H0, if you reject the null hypothesis, you automatically support the alternate hypothesis, HA. And then don't forget to interpret your decision back in the context of the problem. So for this next one, let's say that an economist wants to determine whether there is a linear correlation between a country's gross domestic product, or GDP, and the carbon dioxide CO2 emissions. That researcher took a sampling of countries, calculated their GDP and their CO2 emissions, and put them in this table. So what we're going to do is we are going to use a graphing calculator to calculate the correlation coefficient for the sample R. I uploaded a separate video on how to use a graphing calculator to find your R value. I will leave a link for that video in the description. So using those calculator steps outlined in that other video, and I will also upload the paper instructions on Canvas, you get an R value of approximately 0.912. That same video also shows you how to find the equation of the regression line. So at the same time, you will find the equation of the regression line to be y hat equals 166.9x plus 115.725. So in that last example, if you count it up, there are 10 pairs of data there. So we use 10 pairs of data to calculate an R value of approximately 0.912. And we're going to conduct a hypothesis test to test the significance of this correlation coefficient. And we're going to use alpha equals 0.05. All right, so the first thing we're going to do is we're going to get our null and our alternate hypotheses. Now, in correlation, there's only two of these. So your H0 in correlation is always going to be your rho is equal to 0, which means there's no correlation. Your alternate hypothesis, HA, will be your rho is not equal to 0, which means there is a significant correlation. Since your HA contains a not equal to symbol, this is a two-tailed test. So what we're going to do is we are going to identify our N. Our N was 10 because there are 10 pairs of data. The R was 0.92. That was the correlation coefficient for the sample, and your alpha equals 0.05. Now, since this is going to be a t-test, you need the degrees of freedom. And in a paired data set, your degrees of freedom is n minus 2. So you're going to have 8 degrees of freedom here. So in the t-table, you're going to look up 2 tails alpha under 0.05. So you're going to look up 2 tails alpha 0.05 with 8 degrees of freedom. And you are going to have 2 critical values. Your positive T naught is going to be 2.306. And your negative T naught is going to be negative 2.306. So I'm going to sketch this and shade my rejection regions. So we have negative T naught over here, negative 2.306. And then we have positive T naught over here, which is positive 2.306. Then we're going to turn our R value into a t-score. So your t value is going to equal R, which is 0.912, over the square root of 1 minus your R, 0.912, squared, all over n minus 2, which is 8. You really do need parentheses around this fraction inside the square root, and you do need parentheses around that subtraction in the numerator. If your r is negative, you will need an extra set of parentheses around your r before you square it. A little bit of graphing calculator work later, you should get a t-score of 6.289. So then what you're going to do is you are going to plot this on your distribution. Hold on, I should have shaded the rejection regions. Give me a second. So your rejection regions would be everything in this tail here and everything in this tail here. So that tail you would reject H naught. And everything that's not, oh boy, everything that's not shaded you would fail to reject H naught. So we're going to put 6.289 on our graph. It is way over here. It is so far into the rejection region. There is no question we are rejecting H naught. Oh, goodness. Let's try that again. That's a little better. Remember, when you reject H naught, you are saying that this is false. If you reject H naught, you automatically support HA. If you reject the null hypothesis, you support the alternate hypothesis. The alternate hypothesis was that there is a significant correlation. So, interpreting this in the context of the problem, that means rho, the population correlation coefficient, is significant. So what that means in the context of this problem is that there is enough evidence to conclude that there is a significant linear correlation between a country's GDP and a country's CO2 emissions. Now, another use for regression lines, besides, being able to just look at it on a scatter plot, regression lines are used to predict the y value for a given x value. So as long as that x value is within the range of the original data, you can use your regression line to calculate the predicted y value for that given x value. And what you will do is you will plug your given x values in for x in your regression line. So the regression line that we found a few slides ago was y hat equals 166.9x plus 115.725. So we're going to take these given GDPs and we're going to use our regression line to predict the expected CO2 emissions for each GDP. So for this first one, 1.2 trillion, I'm going to plug 1.2 into my regression line in for x. So I'm going to get y hat, my predicted y value, is equal to 166.9 times 1.2 plus 115.725. Then a little bit of calculator work later, you get y hat is equal to about 316. So what this means is that for a country with a GDP of $1.2 trillion, we expect their CO2 emissions to be about 316 million metric tons. So then for these next two, you can predict the expected CO2 emissions for these given GDPs by plugging 2.0 in for x in your regression line, which will give you a y hat of approximately 449.525 million metric tons. So that would be the expected CO2 emissions for a country with this GDP. And then for 2.5 trillion, you're going to plug 2.5 in for your x in your regression line to give you a y hat of approximately 532.975. So what that would mean is that for a country with a GDP of $2.5 trillion, the expected CO2 emissions would be 532.975 million metric tons. Now keep in mind these are what are expected. Remember, there can be differences between what we expect their CO2 emissions to be and what their actual CO2 emissions would be. That is called a residual. That gap between the observed Y value at the point and the predicted Y value on the line. So that is it for correlation and linear regression, and that is it for this statistics course. So thank you all so much for watching. It has been a pleasure having you all in class. I've really had a lot of fun this semester, and I hope that these video lectures were valuable for you. Thank you all so very much for watching. It means a lot to me that you've watched these because I've put a lot of time and work into them. So thank you very much for watching. I hope that these were valuable. If you have any questions, please feel free to email me. And remember, the graphing calculator steps are both in a separate video and the instructions are posted on Canvas. So thank you all so very much for watching, and I will see you guys later. Bye-bye.